Hello, welcome to the presentation of my master's thesis titled No Labels, No Problem, a study in evaluating the performance of graph-based machine learning models on EEG data with self-supervised pre-training. Now, what does all that mean? Let's get into it. The first thing we should cover is probably the idea of self-supervision or pre-training. And you can imagine that on the task that you actually want the model to be good at. For example, let's say you want it to predict really well if a review on the website is positive or negative, right? Is a bad review or good review, but you don't have many reviews. Let's say you have 1,000 reviews, and you don't want to train this entire model to first get an understanding of language, of how language works, what are good words, bad words, and then eventually get to the point where it can do the classification problem, because we just don't have enough data. So what self-supervised sorry, self-supervised pre-training allows you to do is to take this raw training data and generate the, the, the ground truth from the data itself. So for example, on the picture on the right here, what you do is you say, hey, learn how to predict what this masked word is. What is the word that I have taken out from this sentence? And then the model will just churn through all these thousands and thousands of sentences and learn, okay, what should be there, what should be where. And then once the model has learned this underlying representation of language, you can take that entire model, take it into a different task, as you see on the left, give it a new sentence, say, this movie is awesome, and then ask it to predict is it positive or negative. The prediction part that does the positive negative will be sort of plugged on to this pre-trained neural network and have it do the classification correctly later on. So the same idea is what we're going to apply to EEG signals. Now, the issue here is if you take a sentence, it's quite easy to understand that there are noticeable, like understandable chunks of the sentence, like word units, words themselves, syllables, these kind of things. But when it comes to EEG signal, it's quite tricky to actually make it into a discrete unit. But best we can do in this situation is sort of like we just chunk it up into different blocks. We call them epochs, different little time blocks. And the task that we actually care about for this thesis is to be able to classify if a EEG signal comes from someone with ADHD, or is someone who's healthy, or someone who's been diagnosed with major depressive disorder. And this is the task that you want the model to be good at. This is a really big problem in psychiatry and computational psychiatry in general. This problem that people spend many days, months, maybe even years trying to get properly diagnosed, try to find the right treatment, and it can be expensive and slow and quite demoralizing. And I can speak from personal experience. This is not fun. So what we're trying to do with this project is to develop new, better ways, more robust ways of extracting data from limited data sets and then generalizing them to a more specific task, specifically the task of classifying psychiatric conditions. So for this project, I have 3 different tasks. Two of them are the pretext tasks of the pre-training, and then one of them is the main classification task. This is I take this task directly out of a paper by Lee et al., who use this task for emotion classification, but we use this here for classifying psychiatric conditions. So the 2 tasks and the models I will describe in the next slide. But generally speaking, this is the strategy. So we take the raw data, we break it up into chunks, we convert them into frequency representations, and then we have a model solve multiple different related but not exactly the task we want problems. And then once we've trained that representation generating model, we take it and then we move it to a different domain and we ask it to actually solve this problem for us. I use a couple of different ways of doing this, and I will get to that later. On top of this, we also want to understand how graph neural networks can help bring in more domain knowledge into this problem. So how we do that is basically by trying to teach the model that there is some graph structure in the brain. So for example, you have an EEG cap on the head, and we have different nodes, different electrodes, on the scalp, and these electrodes are of course connected. They're either by connected by proximity, or they're connected by the functional behavior of the brain. So we will first transform this data into a graph representation, which we will give to the model, and then use that to train the neural networks. So generally the goal of this project is threefold. First, to check check the effectiveness of self-supervised pre-training with graph neural network datasets. Graph neural networks and graph representations of data to train a machine learning model. And second, to investigate the effectiveness of different strategies of dealing with very small data sets, which are often imbalanced. So we try a weighting strategy, which is basically at train time, we tell the model that, hey, mistakes you make on minority classes should be weighed a little more than the mistakes you make on majority classes, because majority class appears a lot. And then the other strategy is we are going to just rebalance the data set, basically take out most of the majority class and then make sure everything has the same distribution. And this work I'm building on work by a previous master student, Stuart Smolders, and using his data set, so we have something to compare to. And finally, to do all this, I developed a fairly robust automated preprocessing pipeline to supplement some of the existing code that the authors provide of the original data set, which is outdated and it doesn't really work that well. And I add some new features, so I'll describe them more later in the next slide, but these are the general goals of this project. So to speak briefly of the model architectures and the tasks, right? So I said earlier that we have two separate pretext tasks. So what are these pretext tasks? So one of the pretext tasks you see if you look at the jointly model and the fine-tuning architecture here, I'll tell you exactly what that means in a second. First, for the tasks, so one of the tasks is that we take a representation of one chunk of the EEG recording. We have n channels and the number of frequency bands, because you remember we turn them into frequency domain representations, and we only care about certain frequency bands, so alpha, beta, gamma, theta, and delta. And so we have a 26 channel by 5 channel matrix, and then we have two tasks. So the first task is we ask the model to predict which permutation was applied to the columns. So we have a set number of permutations for the columns, and then we shuffle them around, and then we ask the model to predict which permutation was applied, a fixed number. Then we do the same thing and the second task is doing the same thing for the rows, except instead of shuffling the rows in random, we shuffle the rows in chunks, where each of the chunks is a specified brain region. So like the frontal region, the central, the occipital, etc. And we ask the model to figure out, hey, which permutation are you looking at right now? So which permutation have I moved? So the idea with these two tasks is to get the model to sort of first get some understanding of the frequency relationships in the brain, the frequency band relationships in the data, and the other is to get some understanding of the different spatial locations in the brain as well. So as it tries to get good at this task, we hope that it gets better at this. It learns these representations. So we train the model on these two tasks in two different settings. So in the middle one, you see is the jointly setting, where we train the entire model on all three tasks. So the third task being actually classifying people as, with ADHD, with MDD, and the other two tasks, we train them all together at the same time. Now, what these tasks have in common is you see this shared feature extraction layer right down in the middle here. And what that does, this feature extraction layer here. So this is a shared feature extraction layer, and the idea is that as this representation learning layer gets trained, it learns something about the way the brain works in a way that helps it get good at all three tasks simultaneously. So we hope that pushes the model to much better performance. And so if you look at the right here, the fine tuning setting, what we do is we train the neural network and the graph representation layer on just the two tasks. We train it really well to get it good, and then we just take this feature extraction layer, move it to a solo task, which is just predicting the 5 main classes, and then we see how good it does. So it's basically this vanilla model. The vanilla model has no graph, has no pre-training, has no self-supervision. Just takes the epochs and channels and um, band representation and just tries to predict straight up what the epoch is, what where the epoch comes from. And that's the only difference. So these are the main settings, right? The three main settings. And as a baseline, we train a standard convolutional neural network called EEGNet. It's very common baseline in deep learning studies for neural networks and deep learning studies for EEG data. So just let's look at some results. And so the train time performance first. It's interesting to note that all the models show a strong amount of overfitting except the fine-tune model. And we have some ideas about why this might be, but we found it very interesting that the baseline model, jointly model, all these models overfit the data quite strongly. Uh, which means they can learn the problem, but their evaluation metrics are far worse. So you can see on the right here, this is five-fold cross-validation, and the error bars here are the standard deviation across five folds during cross validation. You can see like the vanilla model uh, actually peaks a little bit slower than the other two, so it doesn't overfit as quickly, but they do still overfit nonetheless. And we can get to the final results that we actually care about. So I'm skipping I'm skipping a lot of the lot of like detailed analysis that we did that can be found in the paper, just focusing mainly on the main results of the thesis. And here are the main outputs of the models and comparing them between the two different data sets, right? So the first thing we notice is that the best performing model across all across both data sets and both models is the jointly trained model on data set one. And on average, I find that the models trained on dataset one perform much better, like almost twice as good um, almost twice as good in accuracy, but much better in F1 score, macro F1 score across the board. But this is still um, this is still quite interesting because because there's a lot of research and debate on what is the best way to handle imbalanced data, and in this case it looks like it's quite context dependent and problem dependent. Some studies have shown that balancing works really well, but there's been a recent trend towards using cost sensitive balancing, so using weighting, for example, to penalize different losses differently. And another interesting thing to note is that the vanilla model performs like almost as well and pretty close comparison, the overlapping confidence intervals to the jointly trained model, suggesting that the feature extraction capabilities from the graph convolutional neural network, just from the raw data without pre-training, is already quite good at capturing some of the necessary interconnectedness in the data, which you found quite surprising. But another thing to note is that the fine-tuned model performs the worst, even though it doesn't overfit in the final task of classifying psychiatric conditions. It nonetheless performs the worst in all the settings, which is surprising for us. So, what are the key takeaways? The jointly trained model on dataset one performs best. The jointly trained model, it works well on the larger dataset, which is also imbalanced, but we use class weighting to manage that. The results are competitive with other data sets that we compared. So in the report, I compare my results with two other state-of-the-art papers on the same data set on the same task, and this model falls about one standard deviation within all the within the results of those two papers. And actually, we use a much more stringent approach here, because instead of predicting at the patient level, I actually predict at the epoch level. So you can imagine that I've taken all the patients, cut them all up into like little 9.95-second chunks, and then I mixed all these chunks together, and I had the model to predict what each of these things is, which you can imagine is a harder problem than, for example, giving one entire patient, having the model learn the pattern across that patient and then make a prediction. So all these things considered, still performs at state of the art or better levels results. Um, the weight scaling seems to perform better than the undersampling approach. This is actually in line with a lot of the research that suggests that this is actually better for these kind of problems. And the self-supervision benefit is not as clear as we hoped, although we see that the graph representation by itself is strong enough to learn quite a valuable signal. But there are a couple of caveats here that I should mention. For one, when we were training the two tasks, the frequency task and the spatial task, one of the things that we do is that because we want to generate a number of different permutations of the signal, we select for the spatial task, we actually selected a subset of samples that are very different from each other to have in as permutations, following the paper of Lee et al. But for the frequency task, as they did as well, we did not incorporate just the most different permutations in that set. We just included all of them in there. So as a result, the model performed way worse on the frequency task, we believe, than the spatial task. So the future work would be actually to do the same technique on the frequency set, get the most unique collection of frequency permutations, and then have the model train on that. So we might see an improvement on the supervision that way. And also, there are a lot of ways to represent the edges in the graphs. For example, we used the spatial edges following the paper by Lee et al. But you can have edges that are connectivity based, and you can have edges that are learned automatically. And these are all conceivable things that could help the models perform better. And of course, there are a variety of different pre-training tasks. We just used two, for no particular reason other than we wanted, because they seem to work for emotional recognition, and implementing different strategies, especially with contrastive learning strategies. So, for example, where we teach a model to identify if two signals that were altered came from the same person or a different person, for example. All these things can have a tremendous impact on pre-training performance as well. And again, so the performance of the spatial task is going to be affected by this as you can imagine. And finally, just to say a few words about the EG Learn package. One of the biggest problems that there is that researchers face in computational psychiatry and just computational science in general is a difficulty in dealing in reproducibility of research, of a lack of standardized data sets, and people using all kinds of different approaches, different data sets, and it's difficult to compare, it's difficult to make progress. So I took extra care to make this the EG Learn preprocessing part of the package extremely robust and as scalable as possible. So to that end, I've used standardized processing with MNE and PyPrep for robust and customizable artifact removal. I have high performance in mind from the beginning, so everything runs parallelly, enabling quick and seamless preprocessing of thousands of files. It's modular design, so I've put everything in its own place that can be mixed and matched and moved around. It's got I had reproducibility on my mind from the very beginning, so I use a centralized seed management of one command setup to set up the environments, to start the preprocessing pipeline on everything. And the preprocessing setup has been thoroughly tested with PyTest and using defensive programming practices like test-driven development. All these things have been contributing a lot to helping me actually do the analysis and the machine learning part. And finally, at the end of the preprocessing pipeline, you have machine learning ready, PyTorch geometric data objects. And if you don't want graph objects, you can easily generate some other objects. But there's still a lot of work to be done on this. For example, the machine learning part and the model development part needs to be made more robust. First of all, it has to be tested more thoroughly, because I just build the machine learning part and the model part as an example and to complete the main tasks of this thesis. So that has to be done. And yeah, so overall, the hope is with this package that research can be made more efficient and more user friendly, and push this computational psychiatry project forward more effectively. Um, that's it. These are the references. I refer you to my the code for the details, and also the manuscript if you want to look more in fine grained about the details, about the results, about the training approaches and everything. Here I just covered the highlights. So thank you for your time. Yeah, bye bye.